The first one we are going to do here is to find the lines of intersection. What does that mean? So let's take a look here. This is what you get when two planes intersect each other. So lines of intersection you have this when two planes intersect one another. So we are talking about two planes here and they share points and it becomes a straight line. So let's take a look at the geometry in the 3D space. So let's take a look at the figure on the right hand side. We have the blue plane right here, alright, as you can see here, and then we have this pink plane here, and then what you see right here is that they cross each other, and then after crossing they share some same points along this line, and this keeps going, and in the end this becomes a straight line in three-dimensional space. That's why I told you that when two planes intersect each other we get a line, a straight line. So this is straight line in 3D. Straight line in 3D. And we are going to find this equation for the line. And now that we know how to find to express a straight line in 3D, in the end we want this. We want RT equal to vector R 0 plus T vector V. This is what we want. Alright, so once again, in order to construct a line we need a point on the line and this vector V, two items. Why don't we start with the vector V? Right? It's not that hard at all to find this V if you know this trick. And here's the trick. Now that you see the geometry in the space, let's assume that you have this. Let's take a look at the plane 1, the blue plane. Since this is a plane, it has a vector that is orthogonal to this plane, and I'm going to call that vector n1. So this vector n1 right here is orthogonal to the plane, orthogonal to plane 1. And we are going to do the same for plane 2, where it has vector n2 that is orthogonal to itself. n2 right here is orthogonal to plane 2. Once you have these two vectors and you perform cross product between them, right? You try to use right hand n cross n2, n cross n2, and in the end it's going to move into this direction orthogonal to both n1 and n2, and this direction in the end is the same direction for the line. Alright, n1 cross n2 here, make a note, orthogonal to both n1 and n2, and it turns out that this same as direction of line of intersection, which is V. Okay, let me fix my handwriting here. This is bad. Alright, orthogonal to both n1 and n2, and it turns out to be the same as the direction of the line of intersection. Okay, alright, off right here. So this means that V that we want to construct this straight line in the space is going to be the same as n1 cross n2. So here we want to find this V, and it's going to be equal to n1 cross n2. So in order to find V, we need n1 and n2. And let's take a look at what the problem gives to us. We can see that they give us two planes, and it's represented as equations xyz, just like we found earlier in the previous topics. Now, we cannot use this right away because this is equation, and what we need for this v is vector. So we are going to have to translate the equation into a vector that is normal to the plane. I want you to use the trick that I pointed out to you earlier about the coefficient in front of the variables are going to be the same as the coefficient, are going to be the same as the components of the vector n. So here, the first plane, we are going to have this vector n to be equal to, same as the coefficient, 3, minus 6, and minus 2. So without having to do anything, just look at the equation of the plane, we get the normal vector to be the same as the coefficient. Same as the plane number 2, vector n2, the component of this vector are going to be the same as these coefficient. So we have 2, 1, and minus 2 for vector n2. Alright, now that we have these two vectors, we can perform the cross product. So let's do the cross products. We have I, j, k again. Components of the n1, so we have 3, minus 6, minus 2. Alright, components for n2, we have this 2, 1, and minus 2. Alright, so let's do the calculation. Here I have this cross down. So I have 16i. Oh, sorry, 12i. And then next one, j minus 2, 2, and that would be minus 4j. Minus 4j. And next one, okay. Alright, sorry, my pen is a little bit stuck. So here, k down to 3 and 1, so we have 3k. 3k hat. Okay, now cross up, minus in front, so we have minus 12k hat, minus 12k hat, and then we have this next one, minus 2i. So we have minus 2i, and last one here, minus 6j. Minus 6j. So here we have 12 plus 2i, that becomes 14i. Next one, minus 4j plus 6j, so we have plus 2j. Plus 2j. Last one, 3k plus 12k, we have 15k. Plus 15k. Alright, so this is equal to 14, 2, and 15. So this vector v that we want are already done. Now what we need is this vector r, 0. Let's make a note here, vector r0 is a position vector. Alright, points to a point, points to P0 on the line. Alright, so let's put coordinates for this P0, x, y, and z. 0, all of them. So in order to find this R0, we need a point on this line. We need a point on this line of intersection, but at this point we haven't found one yet. We don't have this point. So let's find it by using the equations that we have. We have this equation, and these equations we are supposed to match them. and find a point that is shared on both planes. So here's how it's done. The first thing I'm going to do, right here, make a note, find P0 on the line of intersection. The first thing I'm going to do here is to reduce the variable by 1. I'm going to set z to be equal to 0. Alright, this plane expands infinitely, so for sure it's going to have this z equal to 0 somewhere. So this is the first thing I'm going to do, and what I get from that is this first equation, 3x minus 6y equal to 15. So this goes away because z is equal to 0 now. What about the second equation? I have this 2x plus y, and z goes away, equal to 5. And at this point, I am going to try to solve this equation to get x and y value. So that's the first thing I'm going to do here is to, what about I add 6 right here, multiplied with 6, and same with here. So for this one, I'm going to get 12x plus 6y equal to 30. Now I am going to add these two equations together, so this one and this one. So as you can see here on the left hand side, I have 15x and minus 6y plus 6y, it cancels to be 0, and on the right hand side I have this 15 plus 30, so I have 45. And solving this, I get x equal to 3 as the first component for point P0. Now this is not enough because I need y component as well. So let's take a look at this equation. I have this 2x plus y equal to 5. Now I am going to put 3 in here. Alright, so I have 6 on the left hand side. I move to the other side. I get y to be equal to minus 1. Alright, so this is the y component for this point P0. What about z component? It's already here, which means that combining these three coordinates, we have this three components of the coordinate. We have this point P to be equal to P0 to be equal to 3 minus 1 and 0. And since we need this vector R0, we need to change this P0 into position vector. And we have done this before. So all we need to do is to find the vector that starts from the origin and ends at P0. So equal to terminal minus the initial. Terminal is 3 minus initial is 0. Minus 1 for the terminal, minus 0 for the origin, and same for the last one. So there you go, we have this vector R0. So I'm gonna need more space here, so let me erase this part. Alright, so we want this vector equation for the straight line that represents the line of intersection. Now we know R0, we know t, we leave t as variable, and we know the vector v. So let's complete this. Equal to R0, which is from down here 3 minus 1 and 0. And we have this t variable, we leave it. And then vector v. Vector v in the direction of the line. And we found it to be equal to n1 cross n2, which is right here, vector v. Alright, so that is 14, 2, and 15. You can add them together to be 3 plus 14t minus 1 plus 2t and 15t. Okay, so what you see right here is vector equations for the line. So vector equation. And you can choose to present this in terms of as a form of the parametric line. So let's work on each component of this. So x component, parameterization, x equal to 3 plus 14t. Okay, let me check the number right here if it's correct. Right? Okay, 3 plus 14t. Now y equal to the next component, which is minus 1 plus 2t. And the last one, z equal to 15t. And what you see right here is the parameterization form of the line. Meteorization, okay, all right. Sorry about the space. So there you go. You want to answer as the parameterization or as the vector equation. That's up to you. Now let's move to the next calculation of the angle between planes. So here we have two planes, blue and the pink, and we want to find the angle between these two planes. Well, before we go into this problem and try to find this theta right away, let's try to take a look at some trick that we can use. So the first thing we are going to do here is to find the vector n1, which is orthogonal to plane 1. Alright, this blue plane is plane 1. And then we find this vector n2, which is orthogonal to plane 2, which is the pink plane. Alright, so as you can see here, instead of finding the theta between the angle between the plane directly, we can find this theta between these two vectors instead. So it's going to be the same angle right here. Theta is going to be here as well by using the geometry. So let's try to find the angle between n1 and n2. And that's going to be the same as the angle between two planes. So let's take a look at this example here. What kind of information we have in the beginning. So they want us to find the angle between the planes, and they give us, well, the planes. First plane and second plane. Now we want to find the angle between n1 and n2. So here, find angle between n1 and n2 and n2. And we learn about this in dot product, that we can use one of the formulas to find this angle, right? Between n1 and n2. In dot product, we learn that theta, well, we can use the second formula, which is that n1 dot n2 equal to absolute value of n1, absolute value of n2, cosine theta. And by moving around, we know that theta between n1 and n2 is going to be arc cosine of n1 dot n2 divided by the size of n1 and the size of n2. Right. So in order to find this theta, we need the component of this n1 and n2. So let's find them. Now the thing is, what is given to us are planes. What you see right here are planes, equations. So we need to translate this into vector n that is orthogonal to this plane. And by this point, we know that it's kind of easy to find that vector n, because vector n for this plane number 1 is going to have a component that is equal to the coefficient in front of each variable. So n1 I know right away, 3, minus 6, and minus 2. As for n2, I do the same thing. Look at the coefficients. I have 2, 1, and minus 2. So n right here, I have 2, 1, and minus 2. Now, once I have this, the calculation is easy, right? Cosine, arc cosine, I perform the dot product. First component, 3 and 2, I get 6 plus Next component, minus 6, 1, I get minus 6. Next component, I have this minus 2 and minus 2. Product is 4. So I get this 4 divided by the size of n1 and n2. Now I have to find them. Size of n1 and n2, vector n1 absolute is going to be equal to 3 square plus minus 6 square plus minus 2 square. Alright, so we have 9, 36 and 4. Once you add them, it becomes square root of 49. A good number because it comes out to be exactly 7. Now, absolute value of n2, square root of each component square. 2 square plus 1 square plus minus 2 square. So we have this 8 and 9, square root of 9. Good number again. So we have 3. Now we can just plug in these numbers into what we had earlier, which is 7 and 3. So here, continue to this. Theta is going to be arc cosine of 4 over 21. And you can put this in your calculator and it's going to come out to be 79 degree. So once again, angle between planes, you don't do it directly between planes. You do it between the normal vector. So make a note here, find angle between normal vectors instead. And after that it's easy as long as you know the dot product. Now let's move to, well, the last one of this slide, which is the distance from point to plane. So here, distance from point to plane. We have done distance from point to a line before, and we did some derivation of the formula, and this one is about the same. So I am going to skip on the derivation of this formula that we are going to use, and I'm going to use it right away. If you guys want to know how it works, we can discuss on that later. So here is the formula that we need to use. D, the distance between point and the plane, is equal to absolute value of P0, P1, dot with n divided by its own size. Now let's take a look at each component, what each one of this represents. Alright, P1 right here. P1 right here is the point in space. Any point in space. Just like before, when we work on the distance from a point to a line, we use S, but this time it's written as P1, so yeah, let's use P1. Now P2 right, P0 right here is a point on the plane. So, point on the plane. This is another thing that we need, point on plane. And the term in the back, we have this vector n divided by its own size. This is basically unit vector in the direction of n. So you can see that this is n hat, right? This vector n represents the normal vector to the plane. So it's this, vector n. Alright, n orthogonal to plane. So let's summarize. What do we need in order to find this distance? Oh, by the way, the distance is this. Once again, we have this path that is orthogonal to the plane, right? You can see that this path orthogonal to the plane. All right. I'm going to skip on the proof of this formula. All right. Now let's use it. What we need for this formula is, first is the point on the plane, which is this, P0. Then the point in the space, which is somewhere that we want, and then we want the vector n that is orthogonal to the plane. All right, let's use it. Here down at the example down here, we want to find the distance between the point P1. All right, so this is P1 in space, in 3D space. And of course, they give us the plane, the equation for the plane to be this 3x plus 2y and 6z equal to 6. Right? Now we are going to use the formula right away. D equal to the absolute value of P0, vector P0, P1, dot vector n divided by its own size. All right? At this point, we don't have anything yet because it's given to us as equation, and this point P1 is given to us. We don't have these vectors in the formula, so let's build them. The first one we are going to work on is this vector n, which is a vector that is orthogonal to the plane. And by now we know that we can look for that in the equation itself, and it's going to correspond to 3, 2, and 6, the coefficients in front of the variables. From this, we know right away that this vector n that we want orthogonal to this plane equal to this vector 3, 2, and 6. Alright, so n, no problem here. Well, we need to find this absolute value of n as well, so let's find that. Absolute value of n is going to be equal to square root of 3 squared plus 2 squared plus 6 squared. And we are talking about 36 plus 4 plus 9. This is 49. Square root of 49, and we have the size to be exactly 7. Okay, now we need to work on the vector P0 and P1. We need to find out about this vector P0 and P1. At this point, we only know P1, which is 113. We don't know where this P0 is, but we know what does it mean by this. What does it mean by this P0? It has to be a point on the line, on the plane. So let's find one. The first thing we are going to do is to find point P0 on the plane. Okay, and here's how we do that. We have this equation 3x plus 2y plus 6z equal to 6, and all we need to do is to find some x, y, z variable that makes this equation true. Alright, now that we have only one equation, we have the freedom to set two variables to anything we like. So I am going to set, well, make it easy, right? X to 0 and z to 0. This is arbitrary, you can pick something else. Let's see if I put this into equation and I can make this equation true or not. So 0 is going to go in, alright, and I get this 3, 0 plus 2y plus 6, 0. I want this to be equal to 6. And this goes away, and from this I know that y is going to be equal to 3. I can add this, y equal to, I can add them all, y equal to 3, x equal to 0, z equal to 0. You can try to put these values into this equation and it's going to come out okay. With this, I know right away this point is on the plane. So I can make a conclusion right here that P0 is located at x equal to 0, y equal to 3, and z equal to 0. I have proof that it satisfies the equation. Alright, so with this P0 ready, and with this P1 right here, I can find this vector P0, P1. It's going to be terminal minus initial. Terminal is 1, minus initial is 0, so I get 1. Terminal 1 minus 3, I get minus 2. And last component 3 minus 0, I get 3. And there you go. I have this vector p0, p1 to be 1 minus 2 minus 3. And I can proceed to compute the value for the distance. D is going to be the absolute value of p0, p1. So I have this vector 1 minus 2 3 dot with this vector n. Alright, this vector n we have up here, which is 3, 2, 6, 3, 2, and 6. Alright, and I need to divide all of this. Well, I can just put it at the back. Same thing, doesn't matter. Alright, with the size of n, which is 7. Alright, now let's work on the dot product. First component 3, second component minus 6, and last component I get 18 divided by 7. So here I have, oh, I made a mistake here. Minus 2 times 2, I get minus 4. So for the numerator, I have this 18 minus 1, I get 17, and divided by 7. And that is the distance